We are the Gujarat Technological University. Since its inception over a decade ago, GTU has been empowering young and curating minds to realize their true potential. Over 4 lakh inspired students are enrolled with one of the premier academic universities in India. With more than 450 affiliated colleges in its fold operating across 5 zones of the state, GTU, the International Innovative University, your place to move forward.
Department, SHRI Institute of Technology and Research Center, BARDOLI. Today, I will taught you DC to AC conversion, that means inverter. So, what is inverter? Definition of inverter says that it converts DC source into AC source, or we can say that DC power into AC power by switching the DC input voltage in a predetermined sequence so as to generate AC voltage or current output. So, what is the application of this inverter? The application of the inverter is in UPS, industrial drives, traction, HVDC systems. Okay, everywhere we can use inverter. In our home held appliances, we can use inverter. And what is the basic general diagram of this inverter? The general diagram of basic inverter is shown in this figure. So, what type of there's various type of inverter. So, one is according to the nature of the input source. So, what input we are providing to the inverter? So, first type is voltage source inverter, in which we are providing voltage source as an input to the inverter, and second type is current source inverter. Okay, and another type of inverter are according to the waveshave of the output voltage. That means the output voltage is square wave inverter. If output voltage is square wave, then it is known as a square wave inverter. If output voltage is output voltage waveform waveshave is of quasi square type, then it is known as a quasi square wave inverter. And if the output voltage waveform is in form of PWM, then it is known as a PWM inverter. Okay. So, voltage source inverter and current source inverter. So, first diagram is shown here. This diagram is known for the voltage source inverter, and this is for current source inverter, in which just this inverter is added in series to the DC source to make it as a current source. Next, first type we will discuss today is single phase half bridge inverter. In this inverter, we have 2 switches and 3 wire DC system and 2 diodes. These 2 diodes are known as a feedback diodes. First, we understand the operation of this circuit. These 2 switches S1 and S2 are turned on such a way that the turning on time, or we can say the turning off time of S1 is equal to the turning on and turning off time of the S2 to produce alternating waveform at the output terminal. So its operation is divided into 2 parts, 2 periods. First period is for where switch S1 is conducting from 0 to T/2 period, and period 2, that means when switch S2 is conducting from T/2 to T, where T is capital T is known as 1 by F, where F is the frequency of the output voltage waveform. Suppose we want to produce an output voltage waveform of 50 Hz, and our T time period T will be 1 divided by 50, that is equal to 0.02 second, or we can say that 20 milliseconds. Okay, so this is the output voltage waveform. Okay, so in this case we can say that if S1 is conducting, then output voltage will be positive VDC by 2. Means when switch this S1, when this switch S1 is on, then current will flow from this here to S1 through positive terminal of load, then negative terminal to this O terminal, midpoint terminal O. Okay, so the output voltage in this case, in this period when S1 is on, is equal to plus VDC by 2. At T/2 period, we turn off this switch S1 and turn on this switch S2. When switch S2 is on, the direction of the current is from positive VDC to current entering from the negative terminal of the load. It leaves from positive terminal, then from S2 to again end here. So that the output voltage in this case will be negative of this VDC by 2, or you can say that EDC by 2. So here we can say that when switch S1 is on, the output voltage will be plus VDC by 2, and when switch S2 is conduct, then output voltage will be minus VDC by 2. Our load is resistive type. That means for that our load current will be in phase with the output voltage, or we can say load voltage. So that when output voltage or load voltage is positive VDC by 2, then we here get the positive current. When output voltage is negative VDC by 2, here we get negative current. Okay. From this waveform, or we can say that from this waveform, we can say that we have produced a DC power into, we have converted the DC power into AC power. Okay. So we will see the circuit analysis for this. So first of all, what will be the average output voltage? The average output voltage of this waveform, we can say that will be 0. Why? Because the time period for positive VDC by 2 and time period for negative VDC by 2 both are same. That's why the average output voltage will be always equal to 0. And for RMS output voltage, the RMS output voltage will be what our input, that will be our RMS output voltage, that means VDC by 2. Now, when we talk about inverter, we have to talk about first of all harmonics. What is harmonic? If we say that if we produce this square wave waveform, but this square wave waveform is made up of this multiple frequency harmonic components. Okay, that means this fundamental component, this is third order harmonic component, green waveform. This orange waveform is fifth order harmonic waveform. Likewise, it is made up of third, fifth, seventh, ninth, 11, etc. So how can we find this type of harmonic component? For that, we have to first of all understand the Fourier series. Okay, so we know that for Fourier series, what is Fourier series? We perform Fourier series on that waveform where the non-trigonometric waveform, if we want to convert the non-trigonometric waveform into trigonometric waveform, or else we can say that if we have a non-trigonometric function and we want it to represent this into the trigonometric function, then we perform Fourier series on that function. So Fourier series of any function is known as, suppose we talk about, if we take the voltage waveform, then f of v, that is v a0 by 2 sigma n equal to 1 to infinity an cos n theta plus bn sin n theta, where theta is n omega t. So what is the value of a0, an and bn? So a0 is 1 over pi integration 0 to 2 pi f of v d theta. An will be 1 over pi 0 to 2 pi f of v cos n theta into d theta. Bn is equal to 1 over pi 0 to 2 pi f of v sin n theta. So now, if we take one simple example, just like we have seen in half bridge inverter, suppose our output voltage is VDC and positive VDC and negative VDC, and turning on of switch S1 is 0 to pi and turning on of switch S2 is pi to 2 pi. In that case, we find A0, An and Bn. So in that case, A0 will be 0. A0 is nothing but our DC component, and DC component is, that means we can say that our average output voltage of the inverter, and this will be 0. Because in the, we integrate this 0 to pi VDC d theta, and in pi to 2 pi negative VDC d theta, then it will be 0. And then we will find An, another coefficient of Fourier series, and that will be also 0. And we will find Bn. So Bn as, if we expand that, so we will get Bn as VDC by n pi minus cos n theta 0 to pi plus cos n theta pi to 2 pi. If you put upper limit minus lower limit, or else we can say we have to neglect this negative sign, then we can write it like that, lower limit minus upper limit. That means cos 0 minus cos n pi plus cos 2n pi minus cos n pi. As we know that cos 0 is equal to 1, cos n pi is equal to minus 1 raised to n, or else we can write it as cos n pi. Cos 2n pi is always 1 and minus cos n pi as it is. So we get 2 VDC by n pi, 1 minus cos n pi. So if our n is even integer, that means our n is even integer, then cos n pi equal to 1 and bn equal to 0. If you put cos n pi equal to 1 over here, 1 minus 1 equal to 0, that means bn equal to 0. And if we take n is equal to odd number, then cos n pi is equal to minus 1 and bn is equal to 4 VDC. We get bn is equal to 4 VDC by n pi. How? If you put cos n pi is equal to minus 1 over here, this minus minus plus 1, 1 plus 1, 2, 2 into 2, 4 VDC by n pi. So if we plot that on a harmonic spectrum, for fundamental we get 100% output. That means our desired output is fundamental, means the normalized fundamental frequency component. And third order harmonic is 1/3 of this fundamental component. Fifth order harmonic is 1/5 of the fundamental component. Seventh order harmonic is 1/7 part of the fundamental component. Ninth order harmonic is 1 by n and 9 times the fundamental component, and so on. As we increase the number of number of harmonic order, then harmonic content will be reduced for the square wave waveform. So what we have studied from that, the harmonic spectrum decrease as n is increases, harmonic decrease as n is increases. It decrease with the factor of 1 by n, as we have talked. Even order harmonic are absent. As for even order harmonic, that means for 2, 4, 6, 8, we can say that the bn equal to 0. That's why Fourier series output will be 0. And for any square wave waveform, even order harmonic are absent. Nearest harmonic is third order harmonic. So what is the frequency of the third order harmonic? The third order harmonic frequency will be, if the fundamental component frequency is 50 Hz, then the nearest harmonic, or we can say that third order harmonic frequency will be 150 Hz. Okay. Due to the small separation between the fundamental and the harmonic component, so we have, if we want to eliminate or mitigate, or we can say if we filter out the lower order harmonic, then we have to design a low pass filter for this purpose, to filter out the harmonic content. Now we will see the operation of half bridge inverter with the RL load. If we add the inductive load, or we can say that if we put inductor in series with the resistive load, however the load current cannot, if we recall the properties of inductor, we know that when there is an inductor in the circuit, the load current, or we can say the current passing through inductor, will not change immediately. It will change with the it will gradually increase, or else it can gradually decrease. So operation of the half bridge inverter with RL load is divided into 4 distinct modes, and there in this circuit we will see 2 diodes, D1 and D2 is known as a feedback diode. So this is the circuit diagram. This D1 and D2 are the feedback diode, and rest are the same as the we have taught in the R load. Now mode 1. So mode 1 is from T1 to T2. When in T1 S1 is turned on at instant T1, and the load voltage is equal to the VDC by 2, and the positive load current increases gradually. This load current increases gradually. At T2, the load current is at peak value, or we can say that maximum value. At that time, we turn on this switch S2. You turn on this switch S2 and turn off this switch S1. Due to the same polarity, that means the voltage, output voltage polarity and the current polarity are positive, then that means the inductor in the load will store the energy, and it will release this energy in the later stage. That means in mode 2. Due to the load inductive, the load current direction will maintain even after S1 is turned on. Means, as I said, if we have inductor in the circuit, then current direction will not change immediately. It will gradually increase and it will gradually decrease. So at T2, if we turn on this switch S2, then output voltage will be negative, but direction of current will not change instantaneously. It will change gradual. From T2 to T3 it will decrease gradually, and at T3 it will be 0, and again from T3 to T4 it will again charge in negative polarity to maximum current here. So that in this case, that means from T2 to T3 the output voltage is negative but output current is positive, so that we can say that the inductor means that the load is releasing or load is feedbacking to the lower half of the source, and the load voltage is clamped to the minus VDC by 2, or we can say that in from T2 to T3 the load is providing to the load supplies the source. Now mode 3, from T3 to T4. At instant T3 load current is 0, okay, and it will indicate that the A1, the load is energy, stored the energy and has been returned back to the lower half of the supply. At T3 S2 is turned on. This will produce the negative voltage minus VDC by 2 and a negative load current. Okay, load current reaches a negative peak at the end of this interval, that means at T4, and at T4 we will again turn on S1, or we can say that turn off S2. When switch S2 is turned off, now we will understand this T4, or we can say that from this T0 to T1 period, switch S2 is turned off at instant T4. The self-induced voltage in the inductive load will maintain the load current. The load voltage changes its polarity to become positive, VDC by 2. The load current remains negative, and the stored energy in the inductor is returned back to the upper half of the source, DC source. At T5, that means the load current goes to 0 and S1 is turned. T5 means this here T1. Load current goes to 0 and S1 can be turned on again, and this cycle operation is repeated. So this is the operation of the half bridge inverter with the RL load. So here we can say that this is the equivalent circuit. From this waveform we can say that if voltage is positive and current is negative, then this diode T1 is the current will flow from this diode T1. If voltage is positive, current is positive, that means the current will flow from this switch S1. From T2 to T3, current is positive but voltage is negative. That means the current will flow from the diode T2. From T3 to T4, voltage is also negative, current is also negative. That means the current will flow from this switch S2. Now we will see the instantaneous circuit equation. Instantaneous current IO. So this current IO is derived from this Fourier series, where we have first of all derived the Fourier series for the output voltage VO for VO. So output voltage VO, Fourier series for output voltage VO will be 2 VDC, or we can say 2 VDC by n pi sin n omega t. For current it will be 2 VDC by n pi under root r square plus n omega L square. That means our Zn sin n omega t minus theta n, where theta n is tan inverse n omega L by r. Now we will see another type, that means single phase full bridge inverter. So why single phase full bridge inverter is required? The main drawback with the half bridge inverter is that we require 3-wire DC system, and for same amount of input voltage, if we are talking about single phase full bridge inverter, in which we have used the 4 switches. Likewise in half bridge inverter we have used only 2 switches. But this full bridge inverter is still advantageous for us, because for same amount of input voltage, the power rating for this full bridge inverter is 4 times that of the half bridge inverter. Now we will see the operation of this full bridge inverter. It is the equivalent circuit diagram for the full bridge inverter, where in this case switch S1 and S2 are taken as a one pair, and switch S3 and S4 are one pair. Means when we turn on S1, the S1 and S2 will turn on simultaneously and turn on in same time, and at the same time S1 and S2 will be off. S3 and S4 will be turned on at the same time, and S3 and S4 will be turned off at the same time. If switch S1 and S2 is turned on, then output voltage will be positive VO. like we can see over here. The direction of current will be from positive terminal of the VDC to switch S1, positive terminal of output voltage VO, from negative terminal to switch S2 to the negative terminal of the VDC. In this case, the output voltage will be positive VO. If switch S3 and S4 is turned on, the direction of the current is positive VDC to S3, S3 to positive terminal of the load voltage. That means previously it is negative terminal, now it has become a positive terminal, and this is negative terminal, and switch S4 to negative terminal of the VDC. In this case, we will get the output voltage as a negative VO. Now, Fourier series, we again talk about Fourier series. This is the output voltage waveform for the full bridge inverter. So its fundamental component will be, if we derive the Fourier series like we have seen previously. So Fourier series for this full bridge inverter will be VO can be represented as VO is equal to sigma, N is equal to 1, 3, 5 up to so on, means all odd numbers to N, 4 VDC by N pi sin N omega T. So if we put N equal to 1, we get 4 VDC by pi sin omega T, that we can represent it like that. If we put N equal to 3, that means third order harmonic, the value of the third order harmonic will be 4 VDC by 3 pi. 4 VDC by 3 pi sin 3 omega T, that means it has 3 times the frequency as the fundamental component. If we draw the waveform for fifth order harmonic, we will put N equal to 5, that means 4 VDC by pi, 5 pi, and into sin 5 omega T, and its frequency will be 5 times that of the fundamental frequency. So this is the operation of this inverter. So now we will see the operation of it with the resistor load as I have taught you earlier. So in this case, we can say that for 0 to T by 2, switch S1 and S2 are on, and in that case, when switch S1 and S2 are on, output voltage means load voltage is equal to VDC, and for T by 2 to T period, switch S3 and S4 are on, then output voltage will be minus VDC. So what about the load current? Is our load is resistive load, that means load current will be in phase with the load voltage, or we can say that the nature of the load current will be as same as the nature of the load voltage. Okay. So this is the operation of it, and this is the equivalent circuit diagram for mode 1 and mode 2. If in mode 1, switch S1 is on and direction of current is shown here, and in mode 2, S3 and S4 are on and direction of the current is seen over here. So circuit analysis, average output voltage will be 0, as we can see that from the waveform, that positive from 0 to T by 2, output voltage is positive and time period is equal to the time period of the negative voltage, that means average voltage will be 0, and RMS output voltage in this case will be VDC. The Fourier series for this is summation N equal to 1, 3, 5 up to infinite 4 VDC by N pi sin N omega T. The fundamental component output voltage is 2 root 2 VDC by pi. This is the RMS value of the fundamental component, and nth order harmonic component is V0 fundamental divided by N. So this is the circuit diagram for circuit analysis for the average thyristor current. So when average thyristor current will be average voltage divided by resistance. So in the case of the half wave inverter, average output voltage will be VDC by 2. Then average thyristor current will for that is VDC by 2R. And for thyristor, sorry, my mistake. In this case, thyristor, this is for the full bridge inverter. The average thyristor current will be VDC by 2R. Why? Because the thyristor is conductive. One thyristor is conductive for the half of the period, that means 0 to T by 2, or else it will conducted for T by 2 to T period. Now, average RMS thyristor current will be VDC by root 2R, and the peak value of the thyristor current will be VDC by R. So, here I conclude my lecture. In this lecture, we have taught the half bridge inverter with R load, RL load, full bridge inverter with R load, and the Fourier series expansion of the Fourier series expansion for the is load voltage waveform.